Yeah, so this is,
Yep.
yeah, great. Yeah, sorry. So I'm Leslie Field. I still can get flustered by Zoom, having done probably at least a Zoom meeting a day for the last 2 years. Go figure. So what I got to tell this group, and I think you're all aware, you wouldn't be part of this group today, is climate change is worse and more urgent than they probably know. But there's a lot of promising work underway around the world. And Shomitra and I and Brian and many others here have had the privilege of being in many meetings with people who are doing many different solutions for this. What I've been concentrating on is the problem of ice, and that's what's bringing us together. I tried to depress people with no more than one slide of just how bad it is, but here it is. I mean, there's just so many problems. I live in California, so I'm in the area that's been really hit by droughts, heavy droughts, and huge wildfire dangers. So that's the one that hits home for us. Many people are living in areas of deep flooding and, high tide on Main Street sort of thing in Florida, and, just awful, awful problems everywhere. And in the Himalayas, of course, we're worrying about losing water supplies for over 1.6 billion people. Something that was put out lots of years ago after the IPCC fourth assessment, so I think that was back in 2007, was this brilliant ecologist, Terry Root, widow of the late Steve Schneider, another really well-known environmental figure, both of whom liked when I showed them my early ideas of what I was going to do about ice. She worked with a graphic artist to make this rising thermometer of doom. And what you were seeing was that at low, not much temperature rise, they were talking about risks of extinction of 20% or so of all known species. And when we got up to 5 degrees C of warming, if we got that far, they even the IPCC wasn't dancing around anymore. It was extinction of, and it was something like about half of known species. So it's a big deal. This thing to the right is a more up-to-date version that a guest lecturer of mine in my Stanford class was showing of just what happens as we go further and further above warming and above pre-industrial temperatures, and it's just not good. Everything that we see says that it's even worse than people had predicted and faster. And so it's cost a lot of money already. People say, how can we afford to do anything to prevent? But actually, just in the US alone, it's been something like $2.25 trillion that has been spent since 1980, I think. And this is according to one of the US's big climate looking organizations, NOAA, the National Oceanic and Atmospheric Administration. So these are real results saying it's a big deal. This is how I felt when I learned it. I am in this to help have a sustainable world for my kids, right? And you feel like you're the only person, at least in those early days, between the big truck trying to, hurt your kids. And so what I told the Hilton Head folks, I think is the same mission here. It's really, if you can communicate and learn and teach and lecture and connect people to climate solutions, if you can invent and co-develop solutions, and if you could implement things through extensive collaborations, which is why I'm so thrilled with the work that Shomitra and all of you have been doing of collecting to a team that actually we can get a collaboration that could maybe do something in time, then we've really got something here. And those are, I've been, not getting a ton of sleep, just doing all 3 of those. That's Leslie's early days. You don't need all that. And then this class at Stanford, I was talking about the kinds of lecturers that we've had in the class, some of whom are in the room here today on the Zoom, are really, experts on everything you can think of that really might help communicate and educate a group of students, a broad swath, undergrads through grads, of what maybe they could do. And so one of the starring pieces that I show is, and this made a big impact at this conference I recently spoke at too, is what's happened in the Arctic, to Arctic sea ice. And it's profound. This is a 2-minute film showing, you can see sea ice over 4 years old up here on the upper left. This is the inventory. This is the month and year. As you're clicking through this thing rapidly, this was put together by NASA. And on the right, you see what the age of sea ice, how they're representing. The older the sea ice is, the brighter it is. The younger it is, the darker it is. This very dark is open ocean. So we've had a dreadful feedback loop in the Arctic sea ice inventory, both a big export through the Fram Strait of ice as currents and melting has allowed more and more ice to flow away. And then this more and more open ocean, so that when you get to the winter freeze, which we're still lucky enough to have, you're more and more forming your ice on open ocean rather than on already existing sea ice. And that means that it's not multi-year ice anymore, which means that it isn't very bright. Young, thin ice is not very reflective. So we've been losing our heat shield in the Arctic. And there's, at this point, no natural way back, except to do what we should do for the atmosphere and cool in general. There's no natural solution. And so I started thinking about what on earth could we do to break this terrible feedback loop. You can see by 2008, less and less ice. I mean, just drink it in. It's not good. And we're almost up to present day. This goes to a couple of years ago. So it's pretty dire. And yeah. This is the Beaufort Gyre, by the way, if you don't know that, and this is the Fram Strait. And the Beaufort Gyre was the nursery, the historic nursery of multi-year sea ice. We've done field work, Doug, Tony, and I, up in Alaska, up here, Point Barrow, Utqiagvik, which has been our Alaska testing, but we've never tested on sea ice yet. We've never gotten permission for it. And so that's part of why I'm so excited when Shomitra asked us to look at helping with the Himalayas. We can help people with a short-term, with an urgent problem that's staring people in the face now. We could do some good soon, and we can get permissions because it's clear that there's a problem now, rather than this more abstract, let's save Arctic sea ice because it'll help the whole world's climate, but it's hard to get permissions for that. And so this is a really thrilling thing for us, that we have people who actually want us to go and try this out. And we have good evidence that this should be helpful. This is the summary of what the loss of sea ice is. And then after we show positive results in the Himalayas, should that be the case, we think it will be, from pre-testing that Doug and Tony have been doing, that's really been excellent, then we believe that we should be able to get permissions to actually go to work on sea ice as well. I see Subarna and Dedalina in the room. They are climate modelers who work with us, who help take our small scale. We've been doing very small scale tests on lakes and scale what that means, what the results from that means for what climate modeling tells us could be our impact. Experts in the world, Professor Peter Wadhams, Professor Don Perovich, tell us that this overall change, this loss of reflectivity in the Arctic, is driving climate change, adding something like another 50%. So think of all the CO2 driven emissions, how much higher our temperature is getting now, multiply that by 1.5. That 1.5 multiplication is what's happening because of the loss of sea ice we've had so far, loss of reflectivity in the sea ice and the land ice. Each one is contributing about half to that, helping to drive temperature change. And we used to have about 30% of sea ice cover in the Arctic was old ice, and now it's less than a 1% or so. So these are dire things. And so restoring polar ice could slow, and we're counting the Himalayas as the third pole. While the world urgently decarbonizes, we're not saying you can skip that. You can't. We have to get to more sustainable solutions for energy and fuels. But while we do that, if we don't slow some of these terrible feedback effects, we're in big, big trouble. And there's really not much time left to make the difference. I've been hearing it remarked that the experts, this is the one field where the experts are more worried than the general populace. And you hear things, we've been hearing things for years, well, we've got till 2100, and then, well, we've got till 2050. Well, this next decade is the last chance we have to make a difference. And more recently, I've been hearing, we've really only got 3 years. So whatever you think about this, I get quite alarmed hearing that the experts are even saying that the time is worse. It looks like I have permission to let people, to admit people, and I'm getting notifications for that. So I've just let one more person in. And so what we want to do is we want to create and co-develop possible solutions here. And there's a big framework that you need to consider. And it's not just a technical solution. I am a terminal engineer, degrees in engineering throughout. But I have learned over the years of working in industry and consulting and teaching that you have to consider the whole picture. And so we're really trying to consider the whole picture. What does it take to make a solution that actually will work for people, that actually will work for the particular conditions we're in? And again, this is where it's so exciting to have Soumitra forming this incredible team. You're saying it's oriented towards the left. Okay, hopefully I've got everything set. And then the materials that we're using are hollow glass microspheres. It happens that Doug and Tony in Minnesota are retirees from a company that makes these materials. So I have found myself some world experts. I had, been looking desperately for what's a safe material, and my eye lit on that after a few years of experimenting on a lake within driving distance from here where I had permission. And what these look like is it's just a sandy white powdery material. It's fundamentally a silica bubble, is one way to describe it. Silica glass, though, so it means that it's in a glassy form, very harmless. Silica is one of the most abundant materials in the world, and it's not a kind that would cause silicosis. And so it's a very safe thing. It looks like it will be dissolving over time in water as things melt, and that's good. And this is what it looks like on Tony's pond. So this was a few years ago where we hadn't yet done, we'd gotten a treated area just by hand, putting this down on areas of his self-contained pond that he built when he built his house. And then these were the areas that hadn't been treated. These were intentionally left as control areas, untreated controls. And here was an area that was about to be treated. And we just put this in these little rectangles so that we can square by square put out consistent amounts. This is what bare ice looks like without anything on it. Here's snow. You can't do better than snow for reflectivity. And here's that same patch once we've got that sandy bubbles, silica sandy bubbles put down to make it brighter. And it's an instant brightening, which is really cool. This is what it looks like when you are looking at a drone footage from above over this last season. So Doug and Tony did just such superb work here of getting drone footage, getting measurements put in place while our team really couldn't travel back there much. And so here's what it looks like, the area that we treated this past season. And this was the untreated area at the beginning of the season. So you've got ice on both sides. You can see that the materials made things brighter than the ice to start with. And then over time, this is as things are melting. You can see the melting's coming in from the sides. And you can see even after a snowfall, the materials are staying in place and the difference is there after the snow melts again. So this is snow around the edges of the pond, right? And this is after the snow melts again, and you can see further melting. We're getting in towards the melt season. And this is after this side is completely melted out. And so it goes fairly quick once you've done it. But what we found with some really beautiful analysis that Doug, especially Doug and Tony were doing data reduction, and Doug did a thermodynamic model, really did a great job. Doug, do you want to take over from here? Because this is really gets into your part of what, and we've got a paper that we've worked on that contains these results, and Doug really was first author on that paper and has been driving that. Doug, would you like to take over?
I'm just getting Georgia set up here, so why don't you keep going, and then
okay,
I can answer questions. Okay.
Okay, that's perfect. Thank you.
And I'm Tony has keeping it on mute for now.
Okay, and Tony hasn't joined in yet, I think, right? As he suspected, he wouldn't be able to make it. Yeah, I don't see Tony in the room. Okay. Yeah, I want to give due credit to these guys because they've really been driving this work this last season or two, and it, without much help from our side in California. And it's really been fabulous to watch. So basically, what we've done is we've had instrumentation in there measuring temperatures at the surface and below the surface, measuring snowfall, measuring ice thickness, measuring everything you can think about. And these were some of the conclusions from it, right? That this is showing that on the test side, the blue side where we treated things, once you start getting a melt, you can see lower temperatures on the test side than on the untreated control side. And the action happens after the snow melts, because snow really is quite reflective and quite wonderful. But snow isn't a problem. People have worried for years, well, if you've got snow on top of it, don't you just lose your effectiveness? Well, you're grateful for the extra time you've got before a melt because the snow's there. But once it melts, you've got a melt pond, you've got meltwater underneath. And these materials are intentionally chosen to be floatable. I always wanted something that was going to be able to reflect things from the top of a water column if we were dealing with any water. And that turns out to be a good call. So once we have the snow melted and we've got meltwater in place, these materials are just floating on top, continuing to reflect away. And what Doug found in his thermodynamic analysis, telegraphing the punch here, you'll see it a little bit more later, is what we're really doing is we're keeping the water underneath cooler by reflecting the sunlight away. And that turns out to be a beautiful difference. And it's funny because that's what I used as a metric in California here, where I live in the San Francisco Bay Area. We don't get snow. So I was testing, materials, various options I could think of way in the early days, a decade or so ago, in little tanks on my deck and measuring temperature underneath and saying, if it keeps things cooler, it's more likely to let us preserve snow and ice. And that turns out to be the case. So what's happening is that we're slowing down the melting of the ice from underneath is a very significant part of what's happening. And the ice thickness for test and control, Doug was doing some really great analysis here of 27% reduction in the melt rate for the test section. And that was thickness. And then if you look at volume, so that's thickness and area, something like a 35% reduction. And that's really pretty neat because the increase in reflectivity from these HGMs, these sandy bubbles, are something like a 30% increase in reflectivity. So it's all actually holding together in an interesting way. Here's just sort of the snapshot of Doug's analysis, the 1D thermal analysis. And it's really, it's really holding together. There's still some unknowns from soil temperatures underneath that we would love to monitor better in a future season, but it really was pretty darn. So that's the heat flow from ground, unknown, but it's really holding together quite well. And so these are the key results, right? We increased our daily albedo by quite a bit, basically doubling it. Albedo is reflectivity, right? So the scale goes from 0 to 1, 0 for no reflectivity, 1 for 100% reflectivity. The coating reduced the ice melt by 33%, and they withstand the weathering of a Minnesota climate. And after the snow melt, you brighten the ice surface. We've also done climate modeling. Again, as I said, Subarna and Dedalina, who are here in the room, have done this wonderful climate modeling in the Beaufort Gyre, in the Fram Strait, working on papers for both of those. And the modeling is showing that we really can do some increases in oceanic. If we treated a small strategic area of sea ice, we don't want to treat the whole Arctic, but if we could do a small key area, we could increase top of atmosphere reflectivity, which is profound. And we've worked a lot with an indigenous corporation in Northern Alaska, which has been really terrific. And I think after that, we've gone through, okay. my full circle moment. I started this thing for my kids. There's my youngest kid volunteering with us up in the Arctic. And then along came Shomitra asking, could we use this on glaciers? And it really is a big deal, right? You've got severe problems in the Himalayas. There's risks to the entire world from Greenland as well. And it's, you know, there's a lot that needs to be done. So here's just a little, you know, photo to show my Stanford students. Yeah, this is the sort of thing that we want to address. That was Himalayas. This is Greenland. You know, there's no question that these things are really dire problems. And this is what we're trying to do, collaborate to evaluate and implement some safe, effective solutions. Maybe we'll do some for-profit work to try to help fuel funding for the nonprofit. We'll see about that. So that's really the grand challenges that we're trying to do to bring everything we have and are to save everything we still can. So that was that Hilton Head talk with a Stanford twist as well. I'm going to stop sharing now. We have some other images, Doug. Tony sent recently, ones that I've sent, but maybe the easiest thing is to describe that Doug and Tony, as soon as Shomitra started having workshops and meetings about Himalayas, Doug and Tony started simulating glaciers. And so they wanted to look at the darkening effects on glaciers. And they wanted to do some small test areas to see, could we do any good? And here comes another person to admit.
Just to add
Doug,
that Leslie's point, because what we found that the Himalayan glaciers are getting covered with carbon suits, a lot of carbon suits. And one of the other part of it, besides global warming, the other part which is contributing the acceleration of melting is those carbon suits. So after learning that, Doug and Tony started simulating the glaciers in their pond in Minnesota and started see what the effect of interaction between this hollow glass microsphere and the carbon suits. Just wanted to give you background. Sorry for the interruption.
No, that's perfect. And I've just, if you folks wanted to know more about how it's instrumented and things, I have another slide deck queued up that I could show if you want, but otherwise I will not do that to you.
I think that's a good idea. The few slides, if you can go through and then open up questions. Sure. I think
I'll do that
as well.
Great. Okay, I'll share that one as well then. So that was over here. I think this is the right one. Yeah, yeah, too many slide decks. So this is more Doug, Tony, me, a couple other folks who were working with us on this. And you've seen that slide, you've seen this, you've seen this, and you've seen that. What you haven't seen is how they instrumented this was really pretty neat. There are various pieces of equipment that are very useful trying to monitor. Again, maybe you can't see this so well. Let me make it bigger. So what they've been setting up, because these are very, very handy, brilliant people who are working on this. They've got a measurement unit that's looking at incoming and outgoing radiation, solar radiation in long wave and short wave. And so a net radiometer here. They've got various ways they're trying to measure the ice and snow thickness as time goes on. One is looking from the top down, and you can see if snow is falling on top of the pond surface. You can then look and see, okay, how far away was that? And then there's an underwater sonar looking up, trying to see how thick is the ice underneath. This is a very shallow pond. It's about 100 feet across, maybe 100 meters across. I don't remember. And then they've got temperature strings, which is where a lot of that data that you were just seeing has. And so this is always a challenge for us. In Tony's Pond, which melts out completely every year, if you can hit it in time, get your instrumentation ready and debugged in time, you have a chance to put this in when it's easy. You just get to let it sink, put a little bit of a weight here, space your temperature sensors appropriately, and you can have this down in the water before the freeze for a short string and a long string, so that you can get all the way to the bottom of this somewhat curved pond. Again, this was a homemade pond that Tony made years ago as he was building his house. We always have to put these things on buoys, and we always have to be very cautious about what kind of materials we're mounting them from. In very early days up at the pond in the Sierras in California, the instrumentation volunteer who was working with me was putting, this is not my expertise, putting together this instrumentation. So I've been fortunate the people I've been working with whose expertise it is or has become. But what he tried at first was an aluminum tripod, because that would hold things up very well. And what we found was that as the melt happened, we were drilling a hole into the ice from the thermal conductivity, heating up the metal and then the thermal conductivity into the ice. So you have to be careful. We mainly try to build things out of white PVC pipe basically these days. So a plastic kind of pipe that's, safe. And if you cap the ends, actually will float. And that's actually how the pond is segmented into a test and control area, is that we have this floating pipe here on both ends and then a plastic sheet below it to prevent water flow and communication underneath. How we're going to do that on an existing glacier, I'm not sure. How our materials are going to hold up and be held in place if there's a lot of meltwater and runoff on a slope, I don't know. So those are things that I think we're going to be figuring out in the field. And before we get to the Himalayas, we've had this offer to be working on an Icelandic former glacier with a glaciologist we met when Arctic Circle Assembly is one of the big meetings for people who worry about cryosphere. And that's where we met this glaciologist, and he's gotten us some permissions to work there. And we'll be using the Oxford Principles of Transparency and pre-consent, and we need to do that everywhere. We have learned, even working with a native corporation up in northern Alaska, what we have learned since is we really needed to do broader communication with the community, or some people feel, that they are not being heard. And that is something we're going to be doing everywhere going forward. We're going to be seeking to have broad collaboration and broad information. But we've got permissions to work there up in Iceland, and that's going to be very exciting, and that's going to help us figure out what might work to help if glacial slope and runoff is a problem. So there are unsolved things that we will need. Yeah, this was the side view I showed. Here's the top view. And this was more on that field testing data that I showed you. And a little bit more about timing and all that. And this was the kind of data. There's a lot of data cleaning. I think some of you are experts in knowing all this, so that I'm sorry if I'm telling you things that you already know, but not everybody knows this. There's a lot of fluctuation in data as you're trying to measure things. There's a lot of needing to capture that data and process it later. You need to keep it powered. You need, there's just a lot of information needed, and photos give us a ton of information as well on just what is happening. And so this is an example of some of the data that's been collected, but it's a sample, and it's something also very important, and it takes a long time. Unless it's already pre-installed in some site, it takes a long time and a fair amount of expense to get these things, figured out and lined out so that you get this consistent data that we're showing here. And that was the drone footage again. Drones are very handy. There's that. I think this goes, yeah, this is it. So that might be helpful to get an idea of what sort of instrumentation and such we need. And I think at this point, maybe it is high time I stop talking. Let's have a discussion.
Okay, thank you so much, Leslie. Pretty wonderful, inspirational work.
Thank you.
Opening up for questions. Any questions?
Can
You all are
just,
working. Okay.
Oh, Doug wants to talk.
I
Yeah,
can
Doug.
add a comment, sorry, just got back. There's a pretty good relationship between the albedo on a glacier as measured by various glaciologists and the mass balance. And there's been some studies recently in Canada showing that when you have a decrease in albedo, you get into this negative mass balance with it. And it's not that much. It's going from like 0.4 to 0.2 or something like that. And the idea is if we can just basically restore that albedo on just a section of the glacier, we're not looking at treating the whole glacier even. There's just there's an ablation zone on it where it's melting, which is like about half of the glacier. And we're only looking at, we just want to restore the mass balance. So what's happened is there's more snow melt on the upper part of the glacier, so more ice is exposed and lowering the albedo with it. So we just need to, and it's the same for Greenland, I've done these studies, we just need to restore that section that's changed where the snow melt is now exposing the glacier with it. If we can restore that, just bring it up a little bit with the albedo, then the mass balance will go from negative to neutral, or maybe we can even make it positive. We might be able to, Leslie doesn't, it's a little bit optimistic, but I'm talking about restoring glaciers, like this glacier in Iceland that is no longer a glacier because it's lost so much mass, it's not moving. And I guess if you're not moving, you're just ice, you're not a glacier with it. So there's potential for just treating a little bit of the glacier. It's just even in Greenland, it's just a smaller section than the whole glacier with it, and bumping that mass balance back up to where it should be with it.
Yeah, that's such an excellent point, Doug. And restoration was mentioned to me years ago with the sea ice, work and studies that we were doing theoretically, right? And it's like, oh my gosh, you're right. Certainly in oceanic ice, if you can keep a base layer there through first season and then build on it, yes, you actually can restore glaciers. I love what Doug is finding in the literature here that's saying that perhaps we can restore there too. If there's snowfall, you've got a hope, right? And I think what Shomitra was starting to talk about a bit, Doug and Tony have been mimicking the various darkening agents people are seeing on various glaciers in the world. Some parts of Iceland, there's volcanic ash, so they've looked at that. There's glacial silt in Greenland that darkens things. And then there's soot from cook stoves in the Himalayas, and just soot from pollution as there's more tourist traffic and vehicle traffic. And what Doug and Tony's initial, pre-tests they've been doing on an even smaller scale than the pond, sections near the pond, are showing is that with darkening agents, the HGMs in some cases, hollow glass microspheres, the sandy bubbles, are lighter than those darkening agents as well. And so they're actually brightening, they're showing a really unexpectedly, to me at least, increased effect that's really helpful. So we'll see. The other thing about HGMs that's worth mentioning is that these are widespread commercial products. They've been extensively looked at for safety and such, and they're quite affordable for what they're doing because they've been used in everything, highway striping and marine applications. They're just, there's so many ways people have been using them, so that they're well known, and that means you don't have to bring up a brand new commercial process to do this. There's even one company working on using recycled glass as their feedstock, which fascinates me because that would be even a better source of supply and less greenhouse gas intensive. So sorry, that was additional info, but it's kind of an interesting solution. Yeah, Doug, and Doug's had to go away again. Yeah. People have a lot of commitments. So are there any questions that anybody has?
Any questions? Come on, guys. You must have a lot of questions.
Mitra,
Okay, Shreyans, go ahead.
I'm not sure if this was already covered. I think I probably would have missed it. I heard the Iceland part and everything else and the Arctic conference and everything. I remember, Sumitra, you were at some point talking about a potential site in Nepal that we have either secured or we are going to secure, like, and the permit and everything. What's going on in that direction?
Perfect.
So we are working, we selected a site called Langton Valley, and we are working with a lot of people on that. So Langton Valley is not that far from Kathmandu, and we have people from Tribhuvan University here as well. They are going to collaborate, they agreed to collaborate with us. So we are very excited about that opportunity. So Dr. Sudeep Thakuri and his students are here, and Dr. Santosh Nepal is also from Nepal. So they are going to collaborate. Dr. Inka Kok is here. She is from Germany now, but she worked in Kathmandu with those Himalayan glaciers. So we are going to formulate plans and preparation for the next year field trial. So that will be the next few meetings we are planning to do, engage all the experts who have been working on field in that area for a field trial in Langton Basin. So right now that is the chosen site.
Okay, so does that mean you were looking at Arunachal Pradesh, I remember, and then somewhere in Himachal and whatnot? Have those been canceled? Like, what happens to that?
No, not canceled. Right now the focus is Langton Valley, but there is not much, did not get much traction in Arunachal Pradesh, but I'm hoping to get, because what happened is that in Arunachal Pradesh, because the collaboration would be with the state government, to work with the state government, we need a partner from another government agencies. So we so far had at that time when we were approaching Arunachal Pradesh was from private university called TERI in Delhi. Now we have collaboration from Zoological Survey of India, IIT, and another institute, I'm forgetting the name of the institutes. They're all government institutes. So with that collaboration, we should be able to go to Arunachal Pradesh for joint work there. So, but we have not approached that part yet.
Maybe the Wadia Institute is what you're
Yes,
trying to
Wadia
do
Institute.
there?
Yes, Wadia, exactly. Thank you, Subarna. Wadia. So we have a very good collaboration now. We can approach other government agencies, but right now the focus is Langton Valley for this field trial and for next year. And primarily this is, a concert we are doing, global concert, and the money we generate will go towards the field trial in that particular place. So next year the planning will be.
I have a question. Leslie, thank you very much for your talk and also for the really detailed and neat pond experiments that actually answered some of my questions already. And it's really good to know that silica are floating. I wanted to suggest when you go to Langton Valley, do you think it would be helpful also to put the silica on snow to see whether the snow season could be extended at an altitude of 5,000 meters or so? Because gradually the snow line is also moving up and it influences albedo.
So I'm having a little trouble hearing you, but I think what you're suggesting is that snow, it's just a little bit of static comes through as you speak too, but that there's snow that you're wondering if we put it directly on snow, how that would work?
Yeah.
The snow? Okay, yeah, the bubbles don't seem to be any brighter than snow. So that, but it certainly doesn't hurt. And if the snow actually has soot on it, then there could be a profound effect. So that would be very helpful. I guess we're gonna see, right? We don't actually know exactly what the brightness is to start with there, but that could, what Doug and Tony were seeing there in Minnesota was that if you started out with some carbon blacks, they got some soot that they put on some snow in their area, or maybe it was directly on some ice, and they found a profound effect. I mean, it was it completely melted out if it had any soot on it very quickly. And then if there were the soot and HGMs, it lasted quite a bit longer. And yeah, just profound photos that they've shown. They haven't finished the data analysis quite yet on that, but very promising.
Because the snow itself changes albedo as it ages. The snow changes albedo when it ages. So if the silica could keep it new for longer, then the snow season, I wonder by how many days it could be extended. That could be another valuable application.
Yeah,
That's
that's what I think. I think as the snow starts to age, the bubbles tend to float to the top of the snow. I think as the snow melts, the bubbles even migrate to the surface because they have positive buoyancy with it. So that the bubbles, even from the data we have, even on slightly aged snow, the bubbles are showing a little bit more effect on the snow. There's also, we're finding this interesting behavior in that there's an insulative effect. So the bubbles are keeping the snow a little colder from convection with it. And then that they also, because the bubbles, there's a thin layer of bubbles on the surface, they're increasing the long wave radiation. So it's actually giving off radiating more heat back to the snow, which is really interesting. I can send you a draft of the paper. Maybe that would be helpful to.
That's good. Yes.
Yeah.
And by the way, Dr. Inka Cook did a lot of work with carbon suits in the Himalayas, right? So we learned a lot from from your work.
Yeah, we found it's very bad. We just put grams on, and it really degraded the albedo with it. So hopefully the carbon soot will migrate down, and the bubbles will migrate up. Yeah.
And the bubbles do this interesting climbing on top of each other. They are so hydrophilic that if there's any moisture around, which of course there is once you're starting to get meltwater, they're actually at times forming little pillars there. So one of the approaches that has fascinated me about preserving snow is Sonam Wangchuk, right, with those ice stupas in Nepal and Ladakh region. Yeah, just that idea is so fascinating. And these things are sort of self-assembling their own tiny, microscopic stupas themselves. And you wonder if that's going to help in preserving as well.
Yeah, we also looked at it in India. We did a proposal even for just deploying them on snow for avalanche areas, if we could slow the melting enough to affect the avalanches. So that's a possibility. So we're very interested in learning more on their behavior in snow. And we deploy them. Generally, we've deployed them over snow when there's already a snow layer over the ice, even in Alaska and it's worked fine.
Any comments, questions from Nepal side?
Good.
Yeah, thank you, Soumitra, Dr. Soumitra. Yeah, actually, I have a bit, and thank you, Dr. Pete, for your very wonderful presentation. And we can see clearly the very impressive, result from the lake experiment. That one. I was actually also thinking about the slope of the glaciers in the Himalaya. If we consider the glaciers in the Himalaya, most of the part is covered by the debris, right? And the very small portion, the accumulation zones, they are clean ice actually, and almost most of the clean ice, they are located in the very remote areas, and they are really slopey. I don't know how is the characteristics of that glass hollow glass microsphere. Is We can recollect those hollow glass microscope back later on, or is there any maybe you may already have considered those consequences if we live over there. I don't know what's the characteristics of those
Yes, yeah,
hollow
let me
glass
speak to that
microscope. Yeah,
a little bit. Yeah, if you
yeah.
don't clean up the microspheres, if you don't fence them in, they are made of silica glass, and silica is one of the most abundant materials on the planet. So it's not, it's present in all our ecosystems already. It's in a lot of our food products, actually, at least here in the US, as well. Not HGMs per se, but silica. And it will dissolve. I've been looking into how quickly will it be dissolving into water, and it will dissolve over time. So it's actually used by phytoplankton in the ocean. It's part of, they actually metabolize that, helping to build their little shells. So it shouldn't be harmful if it's getting away. There are more studies being done, but everything we've seen is that there's no harm there. But to keep them in place so that they stay effective it's been a challenge. You can think about using sheet forms of materials, and in the early days I was doing that, but that ends up being so costly, and you're likely introducing plastic to try to do that, and that is harmful in the environment, that becomes a challenge. I'm following a new track right now where I'm thinking one might be able to fence things in rings that way. One thing that's working for us is these are so hydrophilic that unless there's a lot of meltwater running downhill, which would carry them on it, that they would likely stay affiliated. If the snow's staying in place, then they're probably staying in place to be affiliated with that, because they're very light. They do climb uphill even to form those little pillars. But those are questions that we don't quite have answers to yet. And if you know information about flow rates of water and slopes and things like that, we could maybe use to try to start simulating things here, that could be very helpful, because that is one of the big questions for me. And then as far as any harm, we're not seeing it, but we will continue to be on the lookout for it. I have actually, as a first principle on this thing, is first do no harm. And, we're really on the lookout. Is there any kind of harmful effect you can see? So far, no, but we're, if you know anybody that we can collaborate with to evaluate that further, we're always interested in that as well. Does that help? And do you have any sources of information we could get on what we need to simulate, slope wise, flow rate wise?
Yeah.
So we can discuss that, Dr. Thakudi, further on this, in our next meetings. If you could join, that would be great. I'll invite you to the meetings, and we can discuss these things further. And we are going to plan preparation, and we need your definitely help to how we can monitor all the logistics. So we'll discuss this further. So having said that, any other question from the team, from our marketing team, or any other questions? Because I want everyone to understand what we are trying to do and feel inspired by that, feel motivated by it. So that is the whole purpose. And there's a whole team we have here from Healthy Climate Initiative and other organizations to help this. So any other questions? Doesn't have to be scientific. Okay, Leslie, you have done a great job. No question.
Great. I was
Wonderful.
going to mention Fred Litt's interest in cook stove issues, right?
Yeah.
That maybe the team needs to know about.
Yeah, we are talking, Fred and I talking and formulating a plan on that as well. So it will be a separate initiative from this.
Okay, great. Great. Yeah, wonderful. Thank you all. It's wonderful meeting you all, and I'd love to be in touch, especially with the glaciologists, meteorologists here for some of those technical details we're longing to learn before we get there.
So we'll have next Saturday meetings to continue this series in the sense of preparing for trial in Nepal. So I will invite everyone to join, everyone in the sense, not, the HCI, people, the people who are interested in the preparation, those people I will invite, and then continue few sessions to have a robust plan for the field trial. Okay. Thank you so much, Doug, Tony, and everyone who could join at this time. I really appreciate it very much. Thank you. And Paramita, I will talk to you tomorrow. I hope you have, understood to some extent that, what we are trying to do, and we'll touch base tomorrow. Thank you.
Thanks,
Bye-bye.
everyone. Thanks, Dimitri.
Okay, thank you. Thank you, everyone. Thank you.